The muon used to represent it is an elementary particle similar to the electron, with electric charge of -1 and a spin of 1/2, but with a much greater mass. It is classified as a lepton, together with the electron, the tau, and the 3 neutrinos. As is the case with other leptons, the muon is not believed to have any substructure, that is, it is not thought to be composed of any simpler particles. The muon is an unstable subatomic particle with a mean lifetime of 69942200000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 microseconds. Among all known unstable subatomic particles, only the neutron and some atomic nuclei have a longer decay lifetime, others decay significantly faster. The decay of the muon is mediated by the weak interaction exclusively. Muon decay always produces at least 3 particles, which must include an electron of the same charge as the muon and 2 neutrinos of different types. Like all elementary particles, the muon has a corresponding antiparticle of opposite charge but equal mass and spin, the antimuon. Muons are denoted by mu- and antimuons by mu+. Muons were previously called mu mesons, but are not classified as mesons by modern particle physicists, and that name is no longer used by the physics community. Muons have a mass of 700210570000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 105.7 MeV, C2, which is about 207 times that of the electron. Due to their greater mass, muons are not as sharply accelerated when they encounter electromagnetic fields, and do not emit as much Bremsstrahlung. This allows muons of a given energy to penetrate far more deeply into matter than electrons. Since the deceleration of electrons and muons is primarily due to energy loss by the Bremsstrahlung mechanism. As an example, so-called secondary muons, generated by cosmic rays hitting the atmosphere, can penetrate to the Earth's surface, and even into deep mines. Because muons have a very large mass and energy compared with the decay energy of radioactivity, they are never produced by radioactive decay. They are, however, produced in copious amounts in high-energy interactions in normal matter. In certain particle accelerator experiments with hadrons, or naturally in cosmic ray interactions with matter, these interactions usually produce bimesons initially, which most often decay to muons. As with the case of the other charged leptons, the muon has an associated muon neutrino, denoted by nu-mu, which is not the same particle as the electron neutrino, and does not participate in the same nuclear reactions. History. Muons were discovered by Carl D. Anderson and Seth Neddermeyer at Caltech in 1936, while studying cosmic radiation. Anderson had noticed particles that curved differently from electrons and other known particles when passed through a magnetic field. They were negatively charged but curved less sharply than electrons, but more sharply than protons, for particles of the same velocity. It was assumed that the magnitude of their negative electric charge was equal to that of the electron, and so to account for the difference in curvature, it was supposed that their mass was greater than an electron but smaller than a proton. Thus Anderson initially called the new particle a mesotron, adopting the prefix meso from the Greek word for mid. The existence of the muon was confirmed in 1937 by J. C. Street and E. C. Stevenson's cloud chamber experiment. A particle with a mass in the meson range had been predicted before the discovery of any mesons, by theorist Hideki Yukawa. It seems natural to modify the theory of Heisenberg and Fermi in the following way. The transition of a heavy particle from neutron state to proton state is not always accompanied by the emission of light particles. The transition is sometimes taken up by another heavy particle. Because of its mass, the mu meson was initially thought to be Yukawa's particle, but it later proved to have the wrong properties. Yukawa's predicted particle, the pi meson, was finally identified in 1947, and shown to differ from the earlier discovered mu meson by having the correct properties to be a particle which mediated the nuclear force, with two particles now known with the intermediate mass. The more general term meson was adopted to refer to any such particle within the correct mass range between electrons and nucleons. Further, in order to differentiate between the two different types of mesons after the second meson was discovered, the initial mesotron particle was renamed the mu meson corresponds to M, and the new 1947 meson was named the pi meson. As more types of mesons were discovered in accelerator experiments later, it was eventually found that the mu meson significantly differed not only from the pi meson, but also from all other types of mesons. The difference, in part, was that mu mesons did not interact with the nuclear force, as pi mesons did. Newer mesons also showed evidence of behaving like the pi meson in nuclear interactions, but not like the mu meson. Also, the mu meson's decay products included both a neutrino and an anti-neutrino, rather than just one or the other, as was observed in the decay of other charged mesons. In the eventual standard model of particle physics codified in the 1970s, all mesons other than the mu meson were understood to be hadrons, that is, particles made of quarks, and thus subject to the nuclear force. In the quark model, a meson was no longer defined by mass, but instead were particles composed of exactly two quarks, unlike the baryons, which are defined as particles composed of three quarks. Mu mesons, however, had shown themselves to be fundamental particles like electrons, with no quark structure. Thus, mu mesons were not mesons at all, in the new sense and use of the term meson used with the quark model of particle structure. With this change in definition, the term mu meson was abandoned, and replaced whenever possible with the modern term muon, making the term mu meson only historical. In the new quark model, other types of mesons sometimes continue to be referred to in shorter terminology, but in the case of the muon, it retained the shorter name and was never again properly referred to by older, mu meson, terminology. The eventual recognition of the mu meson, muon as a simple, heavy electron, with no role at all in the nuclear interaction, seemed so incongruous and surprising at the time, that Nobel laureate I. Rabi famously quipped, who ordered that, in the Rossi Hall experiment, muons were used to observe the time dilation predicted by special relativity, for the first time. Muon decay. Muons are unstable elementary particles and are heavier than electrons and neutrinos but lighter than all other matter particles. They decay via the weak interaction. Because lepton numbers must be conserved, one of the product neutrinos of muon decay must be a muon-type neutrino and the other an electron-type anti-neutrino. Because charge must be conserved, one of the products of muon decay is always an electron of the same charge as the muon. Thus all muons decay to at least an electron, and two neutrinos. Sometimes, besides these necessary products, additional other particles that have no net charge and spin of zero, are produced. The dominant muon decay mode is the simplest possible. The muon decays to an electron anti-neutrino, and a muon neutrino. Antimuons, in mirror fashion, most often decay to the corresponding antiparticles. A positron, an electron neutrino, and a muon anti-neutrino. In formulaic terms, these two decays are mu minus E minus plus nu E plus nu mu plus E plus nu E plus nu mu. The mean lifetime, tau equals 1, gamma, of the muon is micro-s. The equality of the muon and anti-muon lifetimes has been established to better than 1 part in 104. The muon decay width, which follows from Fermi's golden rule, follows Sargent's law of fifth power dependence on mu, where is the Fermi coupling constant and is the fraction of the maximum energy transmitted to the electron. The decay distributions of the electron in muon decays have been parameterized using the so-called Mitchell parameters. The values of these four parameters are predicted unambiguously in the standard model of particle physics. Thus, muon decays represent a good test of the space-time structure of the weak interaction. No deviation from the standard model predictions has yet been found for the decay of the muon. The expected decay distribution for the standard model values of Mitchell parameters is where is the angle between the muon's polarization vector and the decay electron momentum vector, and is the fraction of muons that are forward polarized. Integrating this expression over electron energy gives the angular distribution of the daughter electrons. The electron energy distribution integrated over the polar angle is due to the muons decaying by the weak interaction. Parity conservation is violated. Replacing the term in the expected decay values of the Mitchell parameters with a term where omega is the Lama frequency from Lama precession of the muon in a uniform magnetic field, given by where m is mass of the muon, E is charge, G is the muon G factor and B is applied field. A change in the electron distribution computed using the standard, unprecessional Mitchell parameters can be seen displaying a periodicity of pi radians. This can be shown to physically correspond to a phase change of pi, introduced in the electron distribution as the angular momentum is changed by the action of the charge conjugation operator, which is conserved by the weak interaction. The observation of parity violation in muon decay can be compared to the concept of violation of parity in weak interactions in general as an extension of the Wu experiment, as well as the change of angular momentum introduced by a phase change of pi corresponding to the charge parity operator being invariant in this interaction. This fact is true for all lepton interactions in the standard model. Certain neutrino-less decay modes are kinematically allowed but forbidden in the standard model. Examples forbidden by lepton flavor conservation are mu-E- plus gamma and mu-E- plus E++E-. Observation of such decay modes would constitute clear evidence for theories beyond the standard model. Upper limits for the branching fractions of such decay modes were measured in many experiments starting more than 50 years ago. The current upper limit for the mu plus E++ gamma branching fraction was measured 2013 in the MEG experiment and is 5.7 times 10⁻13 muonic atoms. The muon was the first elementary particle discovered that does not appear in ordinary atoms. Negative muons can, however, form muonic atoms by replacing an electron in ordinary atoms. Muonic hydrogen atoms are much smaller than typical hydrogen atoms because the much larger mass of the muon gives it a much more localized ground state wave function than is observed for the electron. In multi-electron atoms, when only one of the electrons is replaced by a muon, the size of the atom continues to be determined by the other electrons, and the atomic size is nearly unchanged. However, in such cases the orbital of the muon continues to be smaller and far closer to the nucleus than the atomic orbitals of the electrons. Muonic helium is created by substituting a muon for one of the electrons in helium-4. The muon orbits much closer to the nucleus, so muonic helium can therefore be regarded like an isotope of helium whose nucleus consists of 2 neutrons, 2 protons and a muon, with a single electron outside. Colloquially, it could be called helium 4.1, since the mass of the muon is roughly 0.1 atomic mass units. Chemically, muonic helium, possessing an unpaired valence electron, can bond with other atoms, and behaves more like a hydrogen atom than an inert helium atom. A positive muon, when stopped in ordinary matter, can also bind an electron and form an exotic atom known as muonium atom, in which the muon acts as the nucleus. The positive muon, in this context, can be considered a pseudo-isotope of hydrogen with 1/9 of the mass of the proton. Because the reduced mass of muonium, and hence its Bohr radius, is very close to that of hydrogen, this short-lived atom behaves chemically, to a first approximation, like hydrogen, deuterium and tritium, used in measurement of the proton charge radius. The experimental technique that is expected to provide the most precise determination of the root mean square charge radius of the proton is the measurement of the frequency of photons emitted or absorbed by atomic transitions in muonic hydrogen. This form of hydrogen atom is composed of a negatively charged muon bound to a proton. The muon is particularly well suited for this purpose because its much larger mass results in a much more compact bound state and hence a larger probability for it to be found inside the proton in muonic hydrogen compared to the electron in atomic hydrogen. The Lamb shift in muonic hydrogen was measured by driving the muon from a 2s state up to an excited 2p state using a laser. The frequency of the photons required to induce two such transitions were reported in 2014 to be 50 and 55 terahertz, which, according to present theories of quantum electrodynamics, yield an appropriately averaged value of 0.84848700000000000.84087 plus or minus 0.00039 FM for the charge radius of the proton. The internationally accepted value of the proton's charge radius is based on a suitable average of results from older measurements of effects caused by the non-zero size of the proton on scattering of electrons by nuclei in the light spectrum from excited atomic hydrogen. The official value updated in 2014 is 0.8751 plus or minus 0.0061 FM. The expected precision of this result is inferior to that from muonic hydrogen by about a factor of 15, yet they disagree by about 5.6 times the nominal uncertainty in the difference. A conference of the world experts on this topic led to the decision to exclude the muon result from influencing the official 2014 value, in order to avoid hiding the mysterious discrepancy. This proton radius puzzle remained unresolved as of late 2015, and has attracted much attention, in part because of the possibility that both measurements are valid, which would imply the influence of some new physics. Anomalous magnetic dipole moment. The anomalous magnetic dipole moment is the difference between the experimentally observed value of the magnetic dipole moment and the theoretical value predicted by the Dirac equation. The measurement and prediction of this value is very important in the precision tests of QED. The E821 experiment at Brookhaven National Laboratory studied the precession of muon and anti-muon in a constant external magnetic field as they circulated in a confining storage ring. E821 reported the following average value in 2006. Where the first errors are statistical and the second systematic. The prediction for the value of the muon anomalous magnetic moment includes three parts. Alpha mu edm equals alpha mu QED plus alpha mu U plus alpha mu had. The difference between the G factors of the muon and the electron is due to their difference in mass. Because of the muon's larger mass, contributions to the theoretical calculation of its anomalous magnetic dipole moment from standard model weak interactions and from contributions involving hadrons are important at the current level of precision, whereas these effects are not important for the electron. The muon's anomalous magnetic dipole moment is also sensitive to contributions from new physics beyond the standard model, such as supersymmetry. For this reason, the muon's anomalous magnetic moment is normally used as a probe for new physics beyond the standard model rather than as a test of QED. A new experiment at Fermilab using the E821 magnet will improve the precision of this measurement. muon radiography and tomography. Since muons are much more deeply penetrating than X-rays or gamma rays, muon imaging can be used with much thicker material or with cosmic ray sources, larger objects. One example is commercial muon tomography used to image entire cargo containers to detect shielded nuclear material, as well as explosives or other contraband. The technique of muon transmission radiography based on cosmic ray sources was first used in the 1950s to measure the depth of the overburden of a tunnel in Australia, and in the 1960s to search for possible hidden chambers in the Pyramid of Chephren in Giza. In 2003, the scientists at Los Alamos National Laboratory developed a new imaging technique, muon scattering tomography. With muon scattering tomography, both incoming and outgoing trajectories for each particle are reconstructed, such as with sealed aluminum drift tubes. Since the development of this technique, several companies have started to use it. In August 2014, Decision Sciences International Corporation announced it had been awarded a contract by Toshiba for use of its muon tracking detectors in reclaiming the Fukushima nuclear complex. The Fukushima Dye tracker was proposed to make a few months of muon measurements to show the distribution of the reactor cores. In December 2014, TEPCO reported that they would be using two different muon imaging techniques at Fukushima: muon scanning method on Unit 1 and muon scattering method on Unit 2. The International Research Institute for Nuclear Decommissioning (IRID) in Japan and the High Energy Accelerator Research Organization (KEK) called the method they developed for Unit 1 the muon permeation method. 1,200 optical fibers for wavelength conversion light up when muons come into contact with them. After a month of data collection, it is hoped to reveal the location and amount of fuel debris still inside the reactor. The measurements began in February 2015.